All right. Hello, everybody. My name is John Martin, and today I'll be talking about a GPGPU implementation of Pine's spherical harmonic gravity model. Before I start, I just want to briefly acknowledge and thank my advisor, Dr. Hans-Peter Schaub, for his advice and support of this work. So to begin, spherical harmonic models are quintessential for astrodynamics research and also for other disciplines too. Geophysics and planetary scientists rely on high fidelity representations of the gravity field for Earth and other celestial bodies. And by most metrics, the higher fidelity of the model, the better. We can use those in our applications for increasingly high fidelity trajectory design and constellation planning, dynamics, plenty of interesting applications. But there is one downside for having a higher fidelity representation of the field, and that's they're expensive to extract an acceleration from. As the fidelity of your spherical harmonic model increases, the number of compute terms, the number of operations needed to extract an acceleration grows exponentially. And that's problematic as our community is growing increasingly reliant on simulation, and to become bottlenecked by the fidelity of the gravity model forces us to trade between simulation speed and simulation accuracy. And I think this is a problem that has been recognized, and it's been recognized especially in other gravity modeling efforts, namely finite element, polyhedral, and mascon gravity models. But I'd yet to see anyone attempt to solve this problem for the spherical harmonics representation. So what I wanted to do is look to see if there is a way to implement Pine's spherical harmonic gravity model on a GPU and make use of this parallel hardware to lighten the computational load of using these high fidelity models. So explicitly, my design goals were to create a GPU algorithm that was analytic and faster than the CPU, cross-platform, vendor agnostic, and open source. And immediately we can knock two of these two design criteria out based on the language we choose. Anyone familiar with the GPU compute community recognizes that there are four four languages that are prominent today. I would say the most popular is CUDA, which makes sense. Its API is very straightforward. It's not too steep of a learning curve. So it's a great way to get your start in GPU computing. However, there is a hardware dependence. You can only run CUDA code if you have NVIDIA hardware, and that excludes a large user base. So we've excluded it from our languages. OpenCL is a great language. It doesn't have the same limitations as CUDA, but it has law support for Mac OS, so excluded. Metal is Apple's graphics and compute GPU API, so it's not cross-platform. That leaves us with Vulkan, which is a hot off the press graphics and compute API. It's got a bit of a steep learning curve, but a ton of opportunities for developer optimization, and there's no hardware and cross-platform dependence. So we're going with Vulkan for this application. Now we turn to the algorithm at hand. So first, let's get situated and remind ourselves of the spherical harmonic gravity model. To get an acceleration from this series expansion, you need to take the gradients, and you get an acceleration vector g. And this works well with the exception that it is singular at the poles. So along came Pines, and he suggested a coordinate transformation that removes this singularity. And in the end, leaves us with a very clean, simple expression for the acceleration imparted by these spherical harmonic models provided here at the bottom. And that looks great and doesn't look too daunting until you expand those A1 through A4 terms, and you realize that this is a bit of a hefty computation. And we'll break it down in a few minutes here, but the main takeaway is that there's a double summation, which is expensive to compute, and then the intermediate terms are all indexed, which is to say they have their own formulas and their own kind of labor associated with them. So at least heuristically, you want to believe that a GPU may be able to make this computation a little bit more efficient and easier than if left alone to be done by a CPU. So let's break this down a little bit more. Again, as I mentioned, there seems to be two core routines that occur in this A1 through A4 calculation. There's the reduction, that double summation, and then there's the calculation of these intermediate terms. And I want to look at these each individually to see if they're well suited for a GPU, starting with that reduction. So on a CPU, this represents having to loop through a lower diagonal matrix and sum each term within that matrix. And that's that's an expensive operation. Explicitly, it scales as order n squared, which is to say the higher fidelity the model, the worse it gets. Fortunately, reduction is a problem that has been well studied on GPUs, and I leave reference to this in my paper. But on a GPU, you can imagine compressing this algorithm into, compressing this matrix into a single array and making use of these distributed processors on a GPU to convert this operation from order n squared to order log base 2n, which is a dramatic reduction in arithmetic intensity. So if you want to ask, does GPU seem like an algorithm well suited to be put on a GPU? In this case, absolutely. Now comes the other routine, which is calculating these intermediate terms. And if that's well suited for a GPU is a little less clear. So let's break down these terms for a second. First, you have your spherical harmonic terms, so nothing too scary there. You have a collection of normalization terms, which are computed at the very beginning of your sim and never to be computed again. And then the remainder of the terms are coarsely analogous to terms in the potential. So you have this rho, which is your normalized distance to your mass. You have an A matrix, which is your derivative of the associated Legendre polynomials. And then you have these R and I terms, which are roughly analogous to your sines and cosines in the original expansion. So actually a number of familiar terms, and the only ones we really need to worry about are those Ri and A matrix terms. And if you ask, are these well suited for a GPU? The answer is probably not, actually. And that's because these equations are recursive. And that implies that they needed to be executed serially. And GPUs aren't meant to do serialized work. The whole point is you should distribute this work to be done in parallel, not in sequence. So we need to think about if there's a clever way to do this on a GPU. And before getting to that, I first want to visualize it on a CPU. How does a CPU have to approach these problems? So if you look at that A matrix, we first have to compute all terms along the diagonal. And then we can compute off-diagonal terms, and only then can we compute all subsequent terms. But even at that point, we're restricted to move in a row-dominated way. So you have one processor that, again, has to do an order n squared operation, which is expensive. Now the question is, what should I do with a GPU? And GPUs typically work by having thousands or millions of threads that need to be executed. And each thread has a unique ID. And so for this discussion, we're going to imagine each thread is assigned an index within this A matrix. And we, as the developer, need to decide how those threads are sequenced such that you satisfy these recursion relationships. So we know from the CPU calculation, you need to first compute the diagonal, then you can compute the off diagonal. At this point, you get some developer choice, but I think the easiest thing to program is to continue along the diagonals. And in this case, you continue to satisfy the recursion relationships as you work your way through the A matrix. And this is fine. Analytically, there's no reason we can't do this. Practically, though, this does introduce some challenges and consequences because you're doing it on the GPU. Namely, this approach requires synchronization, and GPUs are designed to perform their calculations asynchronously. So that seems antithetical to the point of putting it on a GPU if you're forcing one diagonal to be computed after the next. So that's a slow, expensive way to do this. Another challenge with this approach is you need to store intermediate calculations that were executed by different threads in memory. And memory operations on GPUs are typically slow. So that's not advantageous for this approach. And then finally, and computer scientists will know I'm not using this term correctly, but this particular approach does not maximize occupancy, which is very loosely a way to say the number of active threads is relatively low. So if you have n squared threads that need to be working, only a small set of them can work at a particular time, and therefore you're not making full use of these asynchronous parallelizable hardware like GPUs. And that's a waste of hardware, and it probably is faster to be done on a CPU. So this probably isn't the right approach. Let's return and ask, what do we really need? Maybe there's a better way to do this. And if you look at these A1 through A4 terms, and you look at what specific indices are needed in the Legendre matrix, you see that you need an index of LM, which is represented by this star, and you need the two adjacent terms to that particular index. And again, the CPU will compute all of these terms, and then it will read those specific indices. And that requires that the CPU do all n squared computations. But a cleverer thing you could do on the GPU is instead only compute the terms that you need. Rather than having the CPU execute all of the terms and then reading, you could have just the GPU execute the very specific blocks and indices that it needs to perform the final summation and reduction calculation. So on a larger scale, the CPU would need to compute all of these terms in the A matrix. But with the GPU, you can have different threads computing just the parts that it needs. Then suddenly that algorithm becomes order n rather than order n squared until the entire matrix is populated. So that bodes well. This is good because we're maximizing occupancy. All threads have work to be done and they're all active. There's no synchronization required, and by association, there's no need to store and load from other intermediate operations from different threads. That isn't to say this is perfect, as there are redundant calculations. Many of these threads on the GPU will traverse that diagonal and occasionally retraverse different rows. And there's also divergence in this approach, and I need to break that down a little bit. So typically GPUs have thousands of threads that need to be executed, and conceptually you want to believe that all of them are getting executed at once, but realistically that actually happens in groups of 32 to 64 threads, depending on what hardware you're using. So that is, if we're trying to compute all of the indices in the A matrix within this red box, you'd expect them to be all computed at the same time. That is only true, however, if they share the exact same instructions, which they almost do. They all have to traverse the diagonal, move to the off diagonal, and then go down row wise. But for different indices, how far they traverse down the diagonal and how far they go in terms of rows are different. And so in that sense, they have divergent instructions. And so not all of these threads will execute at the same time, only the parts that share the same instruction. So that's divergence, which isn't ideal for a GPU. You can navigate this problem if you consider multiple spacecraft, though. So imagine you have 32 spacecraft that each have their own Legendre matrix, and you instead divide your thread groups to only compute a single index, the small red box. Suddenly, all of those terms follow the exact same instructions, and there is no longer divergence. So there's ways to navigate around this problem. So I'm sure there are plenty of other ways you can go about this. This is the one we settled on for this conference, and we're looking into alternatives, but we can move on to benchmarking. Now we have the reduction solved, we have a way to compute these intermediate terms. How does it actually perform compared to the CPU? So to measure that, we simulate a 1 hour orbit with 10-second time step intervals with an RK4 integrator. That amounts to about 1,000 instances of this algorithm that we average over. And then we take the ratio of how long it would take the same algorithm to be run on a CPU as it is to be run on the GPU. And the results are as follows. So for a constellation with nearly 2,000 spacecraft, you see that the speed up ratios, if you can change some parameters, these local sizes, I'll omit discussion for them. You can talk about in the Q&A if you're interested. But the total speed up ratios for a model fidelity of degree 128 are consistently higher on a GPU. So you are always getting speed ups by operating on a GPU with large constellations at high fidelities. Large constellations at low fidelities, the speed up ratios aren't as promising. You see some speed up for the reduction calculation, but consistently no speed up for the Legendre matrix calculation. If you look to smaller constellations, in this case 250 approximately, you still see consistent speed up ratios for both the Legendre matrix and the reduction for high fidelity models, but for low fidelity models, there's no advantage to put this on a GPU. And finally, if you consider just a single spacecraft, in both the high fidelity and low fidelity case, there's really no reason to be computing the spherical harmonic model on a GPU. And that's just the complexity of the problem at hand isn't great enough for you to really take advantage of the full parallelizable hardware. So that's where we stand. Currently, we do have a Pines spherical harmonic gravity model that is outperforming the CPU in certain operational conditions on a GPU. And right now, it seems to work best for high fidelity models with large constellations. We're currently working to optimize this to work in lower spacecraft, or constellations with fewer spacecraft or with lower model fidelities. But much of that work will likely have to wait until Corona virus and the pandemic has settled and we have access to the equipment that will allow us to profile efficiently. But that being said, it can be done, and this is ongoing work, but early results are promising. If you're interested or have additional thoughts or recommendations or want to see the source code yourself, I'd love to chat on the Q&A. Feel free to email me at any point. But until then, thanks so much for your attention, and hope to see you in the Q&A.